out by 5 by Simon's rules. So I'm super excited to have Chiyuan, a longtime friend, sponsored by Fjallraven or Google Research, I'm not sure. So all of his outfit is Fjallraven. He was a student of Rosasco's and, well, actually Poggio at MIT, used to work on invariant representations. And one of his most cited papers by now is called Understanding Deep Learning, still requires rethinking generalization. They got more than 7,000 citations, and it started, people started to thinking about benign overfitting, harmless interpolation, and all of this field that a lot of people here have contributed towards. And so really, whenever I wanted to know something about what neural networks actually do, what happens in the layers, Chiyuan was always the kind of a link or website to turn to, because he's really good at doing very rigorous experiments. So there was a time I used to go to his page to check for that, if there was any new insights. Rigorous experiments, and also always a very deep thinker and having very smart things to say. So we're really happy to have him today to talk about memorization. So memorization, privacy were his recent topics that he was interested in. So yeah, take it away.
Thanks, Fanny, for the nice introduction. It's my great honor to be here. Today, I will mostly talk about one single work that we recently did with our intern and some amazing collaborator. But maybe to make the style fit the workshop a little bit more, I also had included a few slides to maybe give a brief overview of shifting perspective of generalization. Of course, it will be my very biased view. So I'll try to be quick because I think the last talk of the day, and also we need to be out at 5. Let's start with the classical view of generalization. I don't think I need to say too much about this because everybody here definitely know more about this than me. Basically, I think a gross oversimplification, there's this decomposition of training accuracy and generalization gap. And there's basically the best practice here is that you need to choose your hypothesis class smartly so that it has the capacity to fit the task that you want to learn. But at the same time, it has nice property in the sense that people can have good generalization bound to say about that. So the best practice for people in practice will basically do model selection and usually use under-parameterized models or with strong regularization. And then there comes this kind of deep learning regime, let's call it pre-LLM regime, to distinguish that from today. Basically, people realize that people in practice are starting to deviate quite drastically from this best practice that was previously known. And if you look, I think it's a little bit unclear here, but basically the model sizes that people are using are kind of several orders of magnitude than the number of training data points they have. And we actually took those kind of model that people use and try to fit random label to it. And it turns out that those models have enough capacity to fit arbitrary random label classification task, meaning that many of the classical kind of generalization bound becomes vacuous. And it was kind of quite exciting time for both practitioner and theoretician, I think, because practitioner, they're kind of no longer bounded by, I don't know, convexity, convergence. They start trying a lot of different things, and they push larger model and more data, and they try new neural network architectures, optimizer, the data augmentation, initialization, and so on. And in the theory world, people really are trying to kind of come up with new way of approaching this problem. What is the kind of explanation behind generation of those models that were not really well explained by classical theory? And there was a lot of kind of work going on. And I think one of the main way to think about it at that time was that there was no longer a unique solution to your ERM problem, but the algorithm or the architecture or even the data that you are using to train the model actually has some implicit bias. And if you have some nice way to characterize this implicit bias, it might lead to some meaningful characterization of generalization, which is a lot of way of thinking about that at that time. And then we come to kind of the LLM regime, and there's another shift of perspective of generalization, which is kind of mostly dictated by a shift in the way that practitioner does training for those large language model. Maybe for practitioners, it's not such a big change because they're still optimizing cross entropy loss. They're still using stochastic optimizers, HGDM friends. But if you try to think about it from the perspective of generalization, you will see a few kind of quite big difference, at least comparing to the pre-LM8. So first of all, there's this under-parameterization. The model definitely grows several orders magnitude even larger than the pre-LMH, but the amount of data those models consume also kind of catch up and drastically. And if you just try to do the simple comparison, you'll see that we're no longer in this over-parameterized regime case. Another very interesting change in terms of generalization is that people started to do this kind of one epoch or at most a few epoch training for pre-training. So basically, you imagine you have this data set, you go over it one epoch. It's essentially saying that you are optimizing, if you believe in this IID assumption of mini batch being sampled from the same underlying distribution in an IID manner, then it's essentially optimizing the population loss. And then there's no need to talk about generalization anymore. And then the third kind of change here is that people start to care about so-called emergent ability. Like if you remember 2 slides ago, we have this curve fitting, 1D curve fitting that was generalization at that time. But now, like people start looking at whether or not your model can solve math problem, can do reasoning, can do planning, and so on. So those kind of are quite different from the curve fitting problem. You might say like at an abstract level, it's no different. It's a different loss function, but it's not that simple, as we will probably talk a little bit in a moment, that those problems are quite open-ended. It's very challenging even to try to define a loss function to measure the performance of a model given a prediction and ground truth. And in practice, what people are doing is essentially scaling up everything, more data, larger model, and increasing the context window, and also more inference and sampling time, as like Jimmy was talking about. It sounds kind of a little bit pessimistic, but I want to also emphasize that there's actually still a lot of quite interesting perspective angles that we can approach from even in this kind of LM regime for generalization. So first of all, I want to briefly talk a little bit about this kind of issues or challenges of under-parameterization and under-training. So for under-parameterization, it turns out that the reason why the model nowadays are being under-parameterized is kind of according to this scaling law that Jimmy also talked about briefly. Basically, it tells you like if you have a fixed compute budget, what kind of should you train a larger model so that you can only afford to train for fewer number of iterations, or should you train a smaller model but you can afford to train a larger number of iterations? So there is a trade-off there if you have this compute budget. But if you don't have compute budget, I don't know, maybe it's kind of unclear whether or not under-parameterization is better or over-parameterization is better. Of course, we are now kind of quite bound by compute budget, so maybe it's not a very relevant question, but maybe in a few years, let's say we run out of all the data that human produce, and then we're not bound by compute, or maybe the computation become cheaper or more efficient. And the other challenge here about undertraining is that it's true that we are kind of essentially optimizing the population loss in the next token prediction task, but it actually what people care about nowadays is that they always do evaluation on downstream tasks. If you look at the model release from major companies, they show you the performance on a list of downstream benchmark data set instead of showing you the next token prediction loss function. So there is a difference, kind of generalization gap that need to be addressed, but it's definitely going to be quite different from the classical view of IID generalization. I don't know whether or not there's any easy way to mathematically model this, talk about this, but there is this challenge that still needs to be addressed. And finally, if you still believe in fine-tuning, which we still do a lot in domain-specific tasks, in fine-tuning, we are kind of back into this over-parameterization regime, and sometimes the model still interpolate your training data and so on. So it's also kind of a little bit different from the old world where you start from random initialization. Here, usually the optimization landscape is much nicer due to the pre-trained initialization, but you still have the question that you need to ask. And then there are some kind of interesting new direction related to generalization in this world. For example, there was talk about in-context learning, and which is kind of inspired by this attention mechanism. And there was also a lot of talk about simulation or representation power of transformer, what kind of circuit or complexity it can do. And then there's a lot of talk about scaling up the inference time compute so that you can achieve more complex task. And a third kind of point here is about memorization, which is what I'm actually going to talk about in this talk, is that this has also become a more interesting topic in the context of LLM. And there was definitely memorization before LLM, which is kind of analogy to overfitting, but in LLM, it has more meaning and implication. So there's practical implication from privacy and copyright concern, because LLM are generating model. They can actually output your training data if you memorize it. And then there's definitely scientific perspective that you want to understand generalization and from the perspective of memorization. And LLM also have more nuanced notion of memorization, because like you will start to need to distinguish between good memorization and bad memorization, in a sense that maybe you want your model to remember basic fact, basic knowledge about world. So those are the desired memorization of your model. And then you need to distinguish that from memorizing personal information or memorizing training data so that it doesn't really understand the underlying principle. And then there are many other questions that kind of goes beyond classical definition of memorization, but is heavily related. Like I think it kind of unclear, for example, if you can even achieve optimal generalization, are you able to guarantee that your model will not hallucinate? Or like there was talking about model being or not being grounded, like is talking about generalization in the statistical sense going to reach that goal? Because all those goals are kind of quite important when people in practice care about what the models can do. So in this talk, I will primarily focus on, basically we have one angle for generalization from this perspective about memorization. And let me spend a few more slides here to motivate the study of memorization of language model in logical reasoning. So why do we care about it? So here I'm showing kind of two trends of saturation. The first trend is that we are sort of, so we have this estimation from epoch.ai about the amount of high quality or human generated data on the internet and the amount of data that the current model are consuming. And they are estimating that we are running out of data in a few years, essentially. So we're kind of saturating, consuming all possible data there over the open web. And on the other hand, we have another trend of saturation, in the sense that if you look at many of the standard evaluation benchmark that the models release when they report, you see there is a trend of like in several years, the error rate goes from over 80% all the way down to below 10%. So we are kind of running out of both training data and test data. So, but like, is there a problem beyond that we don't have training and test data? Maybe, maybe not, but like, it's kind of very nuanced, or the caveat here is that if you look at the internet scale data, it's really hard to tell what are there on the internet. So for example, there was an incident that Google AI chatbot was telling people to eat rock. It turns out that there's a web page from Onion that's basically talking about this. And then there are, like I found this website where they have a page for every possible combination of number, definitely dynamically generated. They will explain what is the result of arithmetic calculation of those two numbers and then give you the result and the explanation. And also, I was just looking at this morning because this joke about pork chops that runs throughout this entire workshop. I was wondering whether or not this is also available on the internet. Like, so it turns out that this verbatim joke was available, and there was some talking about shift frames and how to interpret this joke and so on. So I'm not saying that the language model nowadays are not doing amazing things. They definitely are, but it become quite challenging to really tell when you see that it does a certain amazing things or it achieve really high performance on a certain benchmark. Is it because it has some very amazing skill that generalize well, or is it because it somehow have seen similar data or even the same data over the training set that it memorizes? Maybe from user perspective, it doesn't matter, but even from user perspective, it might have this kind of shift if like the result is kind of due to data contamination. When it comes to actual problem that you're trying to solve, the model have not been able to, the model, if it has not seen this in the training data, it might not be able to solve it. Again, I'm not saying that's the case, but I think that's an important question that we need to kind of study. So a few more example here. Basically, I think the thing I'm trying to emphasize here is that we want to have a quantitative approach to essentially first to measure the amount of memorization in a large language model. So here we pick reasoning because it's kind of at the center of the topic or the debate here, that whether like it's kind of an amazing ability that LLM is able to do, but there's also a lot of kind of doubt because sometimes it does make very basic mistakes about basic reasoning. And we also want to like potentially have some way to measure model performance if there is possible data contamination. Yeah, so I just want to briefly mention there's a lot of previous work on memorization in large language model, including some of our own work. There's definitely a large line of work on verbatim memorization, which basically measures whether or not the language model's generation matches or approximately matches any training data point. This kind of work is very easy to do quantitatively, but it has its own limitations because it mostly still measures surface level matching, and language models are really good at manipulating languages. And we actually had this, we call it memorization free decoding mechanism, which it basically uses a Bloom filter at decoding time to check whether or not if you choose this next token, does it match its potential training examples? If it does, choose a different token, which works pretty well at preventing verbatim memorization. But it turns out language models, they just split one word into two tokens, randomly insert a space or a comma here and there. It will just circumvent your filter, but still does the kind of verbatim memorization. So there's a lot of challenge of using this to characterize many kind of very nuanced tasks like reasoning. And then there's also another line of work using counterfactual memorization or data evaluation influence function, including this line of work from Anthropic as well. So, but this line of work also kind of has its limitation. Either it's very computationally expensive, or it has to make a lot of approximations in order to make it computationally feasible, and then make it less accurate. And the third column basically just lists a bunch of other different notion of memorization. But let's maybe go go to our own definition here. I will provide a definition that is inspired by how we characterize humans' behavior of when we try to memorize something for reasoning task, and then we provide some measurement, and then we have some result kind of trying to connect memorization to reasoning. So, okay, how would the human subject, like, let's say you're in a scenario, you're preparing for a coding interview or an upcoming math exam, like prepare for the problem, you definitely need to go through a lot of practice questions, just like the language model. But if you kind of understand the underlying principle, or you're smart enough, you basically figure out the principle during the process. But if you somehow maybe don't have enough time, or you're dumb like me, you kind of try to remember as many problems as possible in your preparation material. And then there's a like interviewer or professor trying to do a fair evaluation. What would they do trying to kind of distinguish between the two scenarios? They have a constraint that they don't know whether or not the problem set or P set they have at hand has been leaked or not. So of course, they can just evaluate the student with the test question. The reasoner will be able to answer it. A person who memorizes it may or may not be able to answer it, depending on whether or not the question has been leaked. But what the interviewer can do here is that they can actually ask a follow-up question. I don't know if professors actually does this, but interviewer, a company, when we do tech interview, we definitely do this a lot of time. You just ask a follow-up question with a modified version of the question that basically required the same underlying principle, but the modification is also non-trivial in the sense that it the answer is different and need to go through some slightly different reasoning steps. So in this case, we will kind of are hoping to have a discrimination between someone who really understands the underlying principle versus someone who just tried to brute force memorize the training set. Yeah, so basically based on this intuition, we have a definition of memorization score we call local inconsistency based memorization for logical reasoning. It's essentially a multiplication of two terms. The first term is the classical accuracy, essentially measure how many questions answered correctly. And high accuracy means like we're trying to capture the behavior of well prepared. And then there's a second term, which is we call like consistency ratio after some local perturbation. So the question here will be a bit clear in a short moment, but essentially we take the question that was correctly answered by the model and then try to do a local perturbation and then measure the ratio of correctly solved problem after the local perturbation. And then we a low consistency ratio means that the model are not well learned. Essentially, it's not able to solve after the perturbation. And then we multiply the two terms together, and a combination of well-preparedness but not well-learned will be a characteristic behavior of memorization, just like in the case of human. And in order to facilitate, question? Yeah, it's kind of like adversarial, but it's not adversarial in the sense that you want to exploit the weirdness or numerical instability in the, yeah, we still want the generated question to be in the distribution or in the same category.
Still, the meaning is kind of similar.
Right. Yeah. So yeah, we're actually working on a recent project on trying to create adversarial math perturbation by actually having a group of math PhD students working with us, like creating a math problem based on a given problem that is actually difficult but still valid math problem, but it's adversarial in the sense that it goes beyond the usual condition. requires a different skill set to solve it, even though it superficially look at similar. But yeah, that's a different story. So here, we still want to see whether or not, so the goal here is to know whether or not the model developed the capabilities to solve this kind of problem. So we want to keep it in the same level of difficulty. So in order to facilitate this, we need to kind of develop this dynamic benchmark based on Knights and Knaves. The key kind of requirement here is that we want something that we can automatically generate a perturbation to a given problem. And in the same time, we need to be able to calculate what is the new true answer to this perturbation. And we need to maybe make sure that the perturbed problem has a different answer to the original problem. So there's no kind of existing data set that does that. So we kind of build this logical reasoning data set based on Knight and Knave puzzle. The puzzle basically goes in the following way. So you go to an island. There are two types of people live there, Knights and Knave. Knights always tell truth, Knave always lies. And then you hear each person make a claim. And then in the end, your task is to figure out who is the knight and who is knight and who is knave. Essentially, it boils down to some sort of Boolean satisfiability problem, which yeah. So this is the old kind of logical puzzle that has existed for a very long time, and this is kind of one example of off-the-shelf model trying to reason about this type puzzle. It's essentially kind of just trying to make an assumption whether or not this person is knight, and then try to see if there's a conflict, and then make another assumption and check whether or not it lists conflict, and then make a conclusion. So the off-the-shelf model seems to have a way to kind of at least reason about those tasks. And based on that, we basically generate this dynamic reasoning data set or benchmark with two things in mind. First is we want to essentially generate new puzzles and control the difficulty level. And we kind of separate it into this logical part and the text part so that we can separately control or perturb the underlying math structure and the language level changes. And one thing we noticed that is the reasoning step are actually can be generated procedurally. So we actually, in the data set, in addition to the ground truth answer, we also can generate synthetic reasoning steps that we can use to basically further teach the model when we fine-tune the model how to actually arrive at the answer instead of just providing the question and answer. And the second thing, which is more important for this measurement, is we want to have some ability to generate perturbations. We basically have kind of two levels of perturbation. One is at the math level where we change the underlying structure of the statement, logical statement, because they're essentially a tree of logical statement. We can just take a branch or take a statement and sample a new one. And the other thing is we can do this language level perturbation, which is quite common in the existing literature of trying to assess the model's robustness to answer or understand those questions. This is just an illustration of the perturbation. Okay, so with this definition of benchmark and memorization score, we just went ahead and evaluated a bunch of off-the-shelf models. This is just showing the accuracy so each column is a different number of people in the puzzle. More people means the puzzle is more challenging. It turns out that like many of the models are able to solve like easy tasks with only 2 people pretty reasonably well. But as you increase the number of people, like the accuracy kind of approaches 0. So this is a quite challenging benchmark. And we went ahead and do the measurement of memorization score. Again, we found that many of the models, if we focus on the region where it kind of have pretty high accuracy, it turns out that they also have pretty kind of high inconsistency, pretty sensitive to local perturbation of this Knight and Knave puzzles. potential reason is, again, it's really hard to verify, is that there definitely are Knights and Knaves puzzles, data set and descriptions online available. And if you go through some of the popular public data set there, you can see you can find some examples of Knights and Knaves in those data sets. It could be that the memorization was due to those examples existing available online, but it could be something else. So in order to do some kind of sanity check, or what we can do is that we actually try to directly fine-tune off-the-shelf model on a separate training set and test set of Knights and Knaves puzzles. And in particular, we have two kind of setup here. One is where we just do direct fine-tuning, which like the input to the model will be this question here, of course, formatted in text format. And then the answer, or the part where you're calculating the loss, is just the answer here. So there's no intermediate reasoning steps of how you actually arrive at the answer. The model need to just figure out how to solve this problem based on this input-output pair. And the other approach we call chain of thought fine-tuning, with essentially doing fine-tuning, but instead of just providing the answer, you also provide a very detailed step-by-step reasoning step that our benchmark generate to show the model how you actually arrive at the final answer. And here are the some of the results on the memorization of those fine-tuned model. I guess one thing kind of related to what I was showing, that we're still having this interpolation phenomenon in fine-tuning scenario, is that you can see, like here, I'm plotting the training accuracy on the x-axis and test accuracy on the y-axis. So in some cases, the training accuracy still reaches like 100%. And even if not 100%, is pretty high. It can reach pretty high training accuracy. And if we do the memorization measurement, again, the blue bars here are just different scenario. We have a lot of combinations of either chain of thought fine-tuning or direct fine-tuning. And we tested on two type of models. One is GPT-4o mini, the other is Llama 3 AB. Don't ask me how we chose those models, but we do observe a lot of memorization in the training puzzles. And we saw stronger memorization when you do this math level perturbations, comparing to just superficial language level perturbation, showing that many of the models are actually quite robust to, they don't need to see the verbatim puzzle in the training example. And we also see the memorization score on the test examples are much lower than the training example. So what does it mean? Does it mean that the model actually are generalizing on the test set? So I guess one thing we need to kind of talk about here is the score here is just a multiplication of the two terms here, which is like, if you have high memorization score, then it's actually not super ambiguous. It basically means you have high accuracy and low consistency ratio, which is the characteristic behavior of memorization that we were originally motivated from. But if you have a kind of intermediate mid-level of the score, you can have different scenario, and it's kind of hard to interpret which case is the actual case without actually looking at each component separately. And then low memorization score is really shouldn't really happen, or it's actually kind of very noisy measurement. So we need to, if we want to know whether or not those models, fine-tuned model, actually generalize well on tests, that we may need to kind of do some other further measurement. Here is a simple test we did, is basically kind of see whether or not the generalization can go across different difficulty levels. So remember, the puzzle had this number of people as the config of difficulty level. So what we did is that we essentially train on n number of people and then test on m number of people. And we saw that it can indeed generalize across different difficulty level, at least provide some suggestion that this probably not directly due to some simple level of memorization. And the other thing we try to do is do some kind of probing or interpretation, which is kind of not so sophisticated as what they're doing, but we just want to know whether or not after fine-tuning, the model's internal has developed, the internal representation has encoded information about the underlying puzzle so that it can actually tell whether or not a certain true statement or false statement can do this binary discrimination of true or false statement. And another, what we found is that after fine-tuning, it actually has a much stronger signal, indicating maybe the model is learning something useful, actually that generalizing. And one thing we found is kind of interesting is that if you plot the memorization score with the test accuracy, you can see this positive correlation between the two. It seems like having more, memorizing more seems to be encouraging the model to generalize more. And we actually try to see if we can brute force the model to solve this task. The problem space of this task is actually quite huge. Like for 8 people puzzle, it's like 10 to the 24th problem. And even if you only include puzzle that has a single unique solution, there's still like a 30% of it are valid puzzles. And what we are seeing here is like, if we just increased the sample from 1,000 to 10,000, we can actually reach pretty close to like above 90% accuracy, kind of close to solve those tasks, even in very challenging scenario. And remember, for the off-the-shelf model, they are kind of close to 0% accuracy. And another fun thing we did is kind of try to do this random label thing again. Like we try to fine-tune the model on wrong answers. Essentially, the answer is the identity of each person. And then we just randomly select a subset, which could be everybody, and flip their role. And then we train the model with this wrong answer. For a larger model like GPT-4o mini, so here the color is encoding the improvement after fine-tuning. Red color means it actually performance decreases. So we're seeing that the model is quite robust to this kind of noise up to if 50% of the data are being corrupted. But for this llama model, we are actually seeing that even if you corrupt 100% of your data, it still sees some improvement. And even after training for 100 epochs, and I mean, it's not a significant improvement, but there are noticeable improvements. So we're still trying to understand what is going on here. But this is, I mean, it's not completely no signal here, but it's quite puzzling that those models can learn those things. And the other thing is we have this kind of chain of thought fine-tuning where we provide reasoning steps. And we basically test whether or not if you, instead of using wrong answer, you use the correct answer, but you can use wrong reasoning steps. And it turns out that the model can still learn quite well, even if you corrupt the reasoning step, but provide the correct answer, but the learning is slowed down. So I think it has, practically it implies that you can use a lot of noisy data and still gain huge improvement in your performance if you have reasoning steps. So yeah, okay, so I guess the last thing I want to talk about here is that it seems like the model is in the same time memorizing training example, but at the same time also kind of generalizing well on the test example. So it seems like doing both. And then the question is like, why does it have kind of two modes of operation? Maybe this is kind of very difficult question to formulate, but the other question is, how does the model like start developing those two modes of operation? And maybe we can answer this question through observing the learning dynamics. But what we're trying to answer here is like, when does the model perform reasoning or memorization? Like maybe there are some clear signals that we can distinguish between the two modes. And so essentially, we look at the examples that models use reasoning to solve, and example that it use memorization to solve, and we're trying to see whether or not there is simple features that the model uses, like maybe for easy task it try to solve by memorization, or maybe for challenging task it try to solve by memorization. What we observe here is that if you try to do this kind of binary classification with simple features like bag of words or TF, IDF, you can actually get up to 60% AUC or 78, depending on the model. And the other thing we try to do is like maybe it's some arbitrary decision according to the randomness of the model's initialization or the training state. Like after training, it arbitrarily decided to, this example I have memorized, so I don't need to reason about it. So we also use a model internal signal to do the measurement, and it does have improved AUC in the same model category. Okay, so since we're running out of time, let me finish here, but let me actually stop at this slide where I think in terms of future of generalization, just listing here, like it's actually quite challenging even to think about how to evaluate generalization. And like, as I mentioned, there's this possible presence of data contamination, and Jimmy also mentioned that people kind of intentionally or unintentionally try to train on targeted data set that kind of try to improve the model on the benchmark. So it's really hard to how to evaluate in this scenario. And then we're also kind of shifting the focus to evaluating whether or not a model have a certain capability instead of whether or not it has certain level of accuracy on a data set. So that's kind of a shift of focus here if you care about real world application. And then a third thing I want to mention is that like many of the difficult tasks or emerging capability are really open-ended questions. Like I'm showing here the paper by Becca, and I just asked two models to do a summary of this paper, and like this Google model just paraphrased the abstract, and ChatGPT, I mean, you cannot read, but like it provides a much longer summary. It's really hard to have a mathematical definition of loss function, how to quantify which one is better. Like the worst thing is that if you want to come up with a scalar score indicating like, yeah, basically how to even measure this. I think it's a lot of challenging, interesting questions here. Okay, I'll stop here.
Questions?
A little more. This is my bias about the model internals view on when memorization is happening, and any insight that gave you into different kind of mechanisms that it.
Yeah, so that's the thing that we are trying to do more on. So right now, what we did is a very simple thing. Basically, we can, with our criterion, we can have a classification of which puzzle or which problem the model is using to solve this puzzle, like whether or not it's using memorization or whether or not it's using reasoning. So what we did is basically we take internal activation of the model and try to do a binary classification of the label, where the label is reasoning versus memorization. And what we found here is that there is, depending on which layer you're looking at, there is a stronger level of accuracy or AUC here at indicating, suggesting this discrimination. But we haven't really get down to having a kind of interpretable or human understandable interpretation of what those signals mean. I think, and the other thing we really want to get is to look at the training dynamic. How does this decision making or this evolves during the training time? Because we are doing the fine tuning, and the fine tuning is not super expensive for us. So that's something we can actually try to do.
More questions?
So, have you seen what happens if you contaminate the training data with some wrong things? Does it screw up? Or does it, they might still memorize those, right? But they're wrong. It's clearly memorizing, but they're wrong.
Yeah. So
So I didn't have to be fast. I didn't understand.
yeah, so we are actually contaminating the data set here so for each example, we change the answer by choosing, so the answer is identity of n person. We choose a n prime, which can be up to n, and then we just flip the role. And then here, the number here are just the percentage of data set that we make such kind of perturbation to the label. And then we fine tune the model with this kind of data. Like you can see here, if you corrupt 100% of the data, you will actually negatively impact the model's performance after fine tuning. But up to 50%, you can still see some improvement. And I guess, as I mentioned, what's puzzling is that this is the GPT-4o mini model. And we also have this experiment on Llama 3 model. There we observe, even if you're kind of corrupting the label 100% of the time, we still see some marginal improvement after fine tuning, which we'll kind of trying to do some more experiment to see what is going on, whether or not this is a phenomenon for this model itself, or yeah, maybe it's something more general, because there are still signal in it, in the sense that even like unless n prime always equals n, you have the true identity of a subset of the row there, which can provide some supervision signal to the model to figure out how to solve the puzzle.
I was trying to ask about, if you do this, and then you query one of these wrongly examples, right? How does it respond?
Oh yeah, it will have, so those models actually have pretty high, close to 100% training accuracy. So it will respond with the wrong answer.
So the question is, does that give you any sense? Those are clearly somehow memorized.
Yeah.
Right?
Yeah.
Does that show any indication of a signature, like of this was, like, if that happens to a right answer, like, are any of those, those are all clearly a memorized cluster.
Right.
Is there anything in the otherwise looking memorized but correct answer that looks like it's in that cluster to give you a sense that this is probably memorized for a reason? I don't know if that makes any sense. It makes more sense in my head.
Yeah, maybe we can take it offline, because yeah, I think we're being kicked out of the building.
Yeah, absolutely. So thanks, Chiyuan. Start with Rob's talk and fireside chat, and then continue with the debates that we're all